In this video, we're going to talk about even and odd functions, which is something you may or may not have studied in Algebra 2. Now, the thing about an even function is that it's got this property that f of negative x is just the same as f of x. And if we think about that, like on a graph, what that means is that it's going to have symmetry around the y-axis. So suppose we had these 2 points that were on the graph of f of x. And we think about f of negative x. Well, if we've got this x here, and we think about negative x, and it's got to have the same output, the same y-coordinate, okay, we'd have that point over here. If we did that for the other point on the graph, okay, we've got this x, we think about negative x, the same output, same y-coordinate, we can see that this graph should be, symmetric around the y-axis. And that there is just an example of what the graph of an even function could look like. And an odd function, that's going to have the property f of negative x is the negative of f of x. So again, if I was to think about 2 points on the graph of f of x, and I would say, okay, f of negative x is the negative of f of x, okay, I'd think about, okay, well, that first x coordinate, think about negative x. Okay, f of negative x is the negative of regular f, so the y-coordinate, the output has become negative, and so I put that down there. Then do the same thing for the second point. Okay, you got that x, get the negative of x, and then the output is going to be the negative. We can see that it's kind of reflected across the origin. And one thing I will say is that if you've got an odd function and it is continuous everywhere, then it has to go through the origin. Okay, because if it didn't, you can still have this property, by having graph that would, approach the y-axis on one side and the negative part of the y-axis on the other side, then it would be discontinuous. But that's really not going to be part of AP Precalc. All right, we do have this fact down here that says, a polynomial function is going to be even if it has only even exponent terms, and then it's going to be odd if it has only odd exponent terms. And I think I'm going to be, showing you what that means in terms of the algebra, just like with some examples right here. So determine whether the function is even or odd by analyzing f of negative x. This is what we would consider being algebraically determining these things. So we're going to look at f of x, and we're going to consider f of negative x. So wherever I see x in the formula for f, I'm going to replace it with negative x in parentheses. So negative x taken to the sixth power minus 2 times negative x squared minus 8. Okay. Now this one time I'm going to, kind of be really intentional and show you all the steps, but, moving forward, I'm going to just kind of say, all right, well, if I'm taking negative x squared, that's going to be the same as positive x squared. But the reason for that is, okay, well, this is going to be negative x to the 6th. Well, negative x is negative 1 times x. And if I'm taking negative 1 times x to the 6th power, I can say that's negative 1 to the 6th and x to the 6th. Because if I multiplied it out, I'd have, negative x times 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 negative x 6 times. So I'd have 6 negative 1s and 6 x's. And that's why I can distribute the exponent over multiplication in a way that I can't over like addition, right? Okay, so minus 2 times, okay, negative x squared is going to be negative 1 squared times x squared, and then I'm still subtracting 8. Okay, and what you need to know in this class is that, negative 1 to the 6th and negative 1 squared, those are positive 1. So this is going to be equal to 1x to the 6th minus 2 times 1x squared minus 8. Now look, f of x was equal to f of negative x, so we conclude that f is an even function. Now, what I might add onto this is that, looking at the powers of the terms when I had the polynomial written in standard form, that was x to the 6 minus 2x to the 2 minus 8. And if we think about the total number of x's there on that 8, that would be 0 x's. And if I looked, thinking about that fact I just mentioned earlier, at that 0 and that 2 and that 6, these were all even powers, and as a result, my polynomial was even. So if I go down 1 and I look at this one below that says f of x is x to the 3 plus 4x, and I think about how many powers is just x, that's 1 power of x, I'm going to have all odd powers, and I should expect this thing to be odd. But we're going to show it algebraically here. So we're going to consider f of negative x, and then wherever we see x, we're going to replace it with negative x in parentheses. So that's plus 4 times negative x. Right, well, if I take negative x to the third power, I'll be having negative 1 to the third, and x to the third, plus 4 times negative x, that'll be minus 4x. Yeah. And then negative 1 to the third, that would be negative 1, so I have a negative x to the third minus 4x. Right, and that's not what I had before, but okay, if I don't have exactly what I had before, there's also the chance that it could be odd, and then I have the exact negative of what I had before, and so if I factor out a negative 1, I'll have the negative of x to the third plus 4x, and so now I'm seeing that f of negative x is the negative of f of x, and that's what it means to be an odd function. So I would conclude that, f is an odd polynomial because f of negative x is equal to the negative of f of x, but I could also have seen that that was going to happen because the exponents on the powers of x, they were all odd. Now we're going to look at a couple that might, work not exactly how you expect. Okay, so you look at this, f of x is 2x minus 4 squared, and I'm seeing all even numbers, so I would think, all right, it's going to be an even function. It's a parabola, it's got that symmetry, it's all good. Okay, but if we go and we plug in f of negative x, we are not going to get the exact same thing we had before. Okay, so we're going to say, all right, f of negative x is equal to 2 times negative x minus 4 squared. And so that would be negative 2x minus 4 squared. And that's just not going to be the same thing as positive 2x minus 4 squared. If you wanted to understand why that was true, you could probably expand both of those, and write them all in standard form, and that might have been probably the best way to go here. But oftentimes we go around and we end up trying to factor out a negative 1 in this type of problem. So that's what I'm going to do. I'm going to say, all right, well, maybe I'm just looking at this as factoring out the negative 1, and I'm left with a 2x plus 4. And that's still getting squared, right? And if I square negative 1, that's going to be positive 1, and so that would be 2x plus 4 squared. Okay? And 2x minus 4 squared and 2x plus 4 squared, they're not the same thing. They're not the exact negative of each other. So this function is going to be neither even nor odd. But if we wanted to see that maybe a little bit more clearly, I might suggest we multiply it out. So, kind of lay it out there, do our FOIL, combine like terms, and get it down to 4x squared minus 16x plus 16. If we do that, and then we look at the exponents right here, second exponent, x to the first, that's a 1 exponent, and 16x to the 0. I've got even and odd exponents both in the standard form of the polynomial, and so that makes me certain that that polynomial is going to be neither even nor odd. And then this one over here, f of x equals x to the 5 plus 1. You see all odd numbers, you would think, okay, that's going to be an odd function. But if we look at f of negative x, we're going to have, negative x getting taken to the 5th power. So that's going to become negative, but the 1 is going to stay the same, right? Because it doesn't have any x's attached to it. So if I take negative x to the 5th power, that's going to be negative x to the 5, because that's an odd number of negative 1s. Then I have plus 1. Okay, so this is not equal to f of regular x. And then if I factor out the negative 1, I'd have x to the 5th minus 1. This is not equal to f of negative x. And in conclusion, I'm going to say that f is neither even nor odd. But, back to the idea of the powers, that had an odd power and an even power together, and that's going to give me neither. All right, the last two I've got of this, determine whether it's even or odd, are not polynomial functions, but they're functions that I want to talk about all the same. And, we don't have to only do this with polynomials. We can do this on a rational function. So wherever I see x, I'm going to replace it with negative x. And to show you that maybe with rational functions, the same rules don't necessarily apply. So I'm going to have negative x on top and x squared plus 1. And I don't know if this looks that way to you, but I could take that negative x and I could write this as -1 multiplied by x time, or divided by x squared plus 1. And so what I'm saying is that f of x is or f of negative x is the negative of f of regular x. I'm going to conclude this is an odd function, but I'm going to not just leave that one there. I'm going to talk a little bit more about this one. I'm going to show you what the graph of this function looks like. If you think about what happens when you plug in x equals 0, you get f of 0 equals 0 over 1, and that's going to be 0. Okay, so the function's graph is going to go through the origin. Okay, when x is equal to 1, I'm going to have 1 over 2. And so I'll put that about right here. If you graph this on Desmos, you can end up saying that's the absolute maximum of the function. There's a relative maximum there, but it doesn't ever go any bigger than that, so that makes it an absolute maximum. And we just found out that this was an odd function, so at x equals -1, I should have y equals -half, and that would probably happen around there. Okay, based on facts about odd functions, that does mean that that's going to have to be an absolute minimum on the graph of f. You can see all this if you graphed it on your calculator, graphed it on the internet or anything. And then it's going to have a horizontal asymptote of y equals 0 because, well, it's, kind of a bigger on bottom fraction. The denominator is growing faster than the numerator, so eventually this thing's going to tend towards 0. Also, it doesn't have any vertical asymptotes because x squared plus 1 can never equal 0. And so the graph ends up looking like that, and that is an odd function because it's got that symmetry over the origin. And the last of these is it even or is it odd type problems is f of x is x times e to the negative x. So I'm going to think about what happens when I plug in negative x for x in parentheses, right? Always in parentheses. X e to the negative x e to the negative of negative x. That's going to equal negative x times e to the positive x. Right, and okay, this might look a little bit like the negative of f of x, but it's not. Okay, because I might point out that, okay, this is f of negative x right here. We can't write this as a fraction at all. I don't have any negative exponents, right? But I would say that f of regular x could also be written as x divided by e to the x. And that is just not the same, nor is it the exact negative of f of negative x. So I'm going to conclude that f is neither even nor odd. All right, and now we're going to need to look at some other examples that are going to be about even and odd functions, but they're going to, use some facts that we really have not talked about in this course, and I don't think we talked about in Algebra 2, and it might have been a long time for you. We're going to need to think about even numbers and odd numbers. And now for a lot of this, I'm going to be, giving you maybe more advanced reasons for these things to be true than you saw the last time you saw them, which, might have been like elementary school or something. So I'm going to just point out that an even number is always going to be able to be written as 2 times n, where n is an integer, and an odd number is always going to be able to be written as 2n plus 1, where n is an integer. I think that's going to be important. Okay, so an even number plus an even number, that's going to be an even number. And you can either understand that by just like thinking about adding even numbers together in your head or looking at the algebra I wrote off to the left. Either way, that should convince you that even plus even is going to be an even. Okay, an odd number plus an odd number, believe it or not, that's also going to be an even number, and I'll just show you why. So the way I think about it is, like you have an odd number and that's an even number plus a 1, and then you add another odd number, which is some other even number plus a 1, and those two ones add together to be an even, then you got an even plus another even. Okay, an even number plus an odd number, that's going to be odd. Kind of for the same reason. You got the even number and then the odd number is an even number plus a 1, so we just have that extra 1 hanging out there, and that's what makes a number odd. Okay, so an even number multiplied by an odd number, well, any even number multiplied by anything, that's going to be an even number. Because it's got that factor of 2 in there. Okay, and so an odd number multiplied by an odd number, it feels like it should be odd. Like 5 times 3 is 15, 7 times 3 is 21. But if we go in and we kind of look at it algebraically and we think about 2a plus 1 multiplied by 2b plus 1, we get a bunch of even numbers plus 1. So it makes a lot of sense. Okay, and any power of an even number, well, that's just an even number multiplied by itself a bunch of times, so that's definitely going to be even. And odd to a power is going to be odd because it's just the same odd number a bunch of times, and an odd number just doesn't have that factor of 2. And since I'm not multiplying in any new numbers, I wouldn't be able to get that factor of 2, and that's why it's going to continue to be an odd number. All right, so the next question is like, all right, here's a polynomial. It's a times x to the p plus b times x to the q, where p and q are integers. So it asks, what conditions would guarantee that f is an even function? And I'll be honest, this is a multiple choice question. We had a hard time replicating. So when I asked this question in class, it's kind of like, okay, well, what could you tell me? Like, what would guarantee that f is an even function? And I'm, looking for a bunch of different answers. I'll be honest, I actually haven't delivered this lesson in class yet, so I'm not sure exactly what answers I'm going to get. I'm sure I'm going to get some better than what I can come up with here. But, f is going to be an even function. The real conditions are that p and q are both even. So that's really the main condition. But I'm going to think of some equivalent conditions as well because, it's probably not just going to say P and Q are both even on the multiple choice question, right? That's, if it was, I wouldn't be prepping you for it right now. I would think that was easy enough that you could just, hear me give the definition one time or that special fact related to even polynomials, and that would be enough. Okay, so I would say, all right, it's. I think we need to go to addition, right? Because even times anything would be even. Like if p was 4 and q was 3, then the product would still be even, but the polynomial f would not be. So I think, yeah, I'm gonna say maybe. But odd plus odd is also even, so I'll be honest, I'm not really thinking of any more, but number theory is never exactly my field of expertise. So maybe there's some out there with the facts we just wrote down, but I think we could have quite a few conditions that would guarantee that the function would be odd. And that will happen if both of the exponents are definitely odd. And I think that we can get that, like if their product is odd, because if their product is odd, they have to both be odd. Okay, P plus Q would necessarily be even, but we could have P and Q both being even numbers and adding to be an even number. Let me think about that. Maybe, yeah, you could say like P squared and Q squared are odd. But that's kind of a stretch. I mean, I could probably have said that about the even one if they have both have even squares. Honestly, I'm not feeling like I'm all that creative on this one. I'm sure that hopefully I'll get better answers, in class. Maybe something else to add to this, but if you know the facts above and you know that and you can reason through the answer choices on that level, then you'll be fine on the problem I'm talking about. All right, so then the question, what do a and b contribute to f in terms of being an even or odd function? Those coefficients of x, they contribute absolutely nothing. All right, those coefficients, those numbers of x to some power, those are just there to distract you. Those aren't really going to contribute anything to being an even or an odd function. All right, now I'm going to take just a couple of minute detour from the original lesson and talk to you about the graph of the y equals the square root of a squared minus x squared, where a is, some integer. It doesn't really fit well anywhere else, but we just decided we were going to throw it in right here. It's something I need you to know for calculus. So the set of all points that are x, y, that are a units away from the origin satisfy the equation x squared plus y squared equals a squared. This used to be part of algebra 2, but it isn't anymore, and so I just need you to know this. What's really going on here on this circle is that it's all the points x and y that are a units away. Okay, and we can think about x and y as like the side lengths of this triangle. And that's why it's going to satisfy that equation over here, that x squared plus y squared equals a squared, is because, the Pythagorean theorem on x and y and a. Now, if we wanted to solve for y to get like a y equals f of x sort of equation for this circle, what we do is we'd start by subtracting that x squared, and we get y squared equals a squared minus x squared, and then we would take the square root of both sides of the equation, and of course we would remember to throw that plus or minus in there, and we get y equals plus or minus the square root of a squared minus x squared. What's really going on here is, we got y equals the positive square root of a squared minus x squared. That's going to give us the top half of the circle, right? Because if we solve for y equals, it's kind of got to be a function, right? In the vertical line test sense of the word. And y equals the negative square root is going to give us the lower half because it's, all those points where y is negative. So it'll be this down here. And, if we just look at the top half and the bottom half of the circle, these are functions. They pass the vertical line test, and then together they give us the whole circle. So if we were asked to write an equation for a circle of radius 3 in the form y equals f of x, okay, we could say y equals plus or minus the square root. A was the radius, so that would be 9 minus x squared. Now, this is a circle of radius 3. I will point out it's centered at the origin, and we're not going to be looking at the equations of circles that aren't centered at the origin for a variety of reasons, but mostly because they're not even necessary in AP Pre-Cal, I don't think. Now, we have looked at, a function that was the square root of a number squared minus x squared when we were finding an inverse function, just a couple lessons ago. But that was kind of a different discussion. That was kind of what sparked the idea in my mind that maybe we needed to talk about these. Now, sketch the graph of f of x equals the positive square root of 25 minus x squared. Okay, so we're going to need an x-axis and a y-axis. Okay, I know that this is going to be a semicircle, and it's going to be the upper half of a semicircle. So I'm going to give myself, more room in y than x, and then I'm just going to draw it as best I can. And just point out, hey, I know that the radius of this thing is 5 because it was 25 minus x squared. Okay, so that's going to be my sketch. And then over here, I'm going to have the negative square root of 1 minus x squared. That's going to be the lower half of the circle. It's going to have radius 1, but I'm only going to be interested in the part where x is between negative 1 and 0, so that would just be a quarter of a circle down there in the third quadrant. Alright, that's going to be enough about the circles for now, and probably for the rest of the course. But let's move on and talk about some extra examples. So the polynomial p of x has a local minimum at x equals 4. So I'm going to actually draw a picture of what I think that might look like. All right, with no loss of generality, I'm just going to assume that local minimum is happening above the x-axis. All right, if p is an even function, then p has a local maximum at x equals negative 4. All right, well, an even function has symmetry across the y-axis. Okay, so whatever behavior I'm seeing to the right of the y-axis, I see the exact same thing to the left. Okay, and if that's the case, though, that looks like I should be having a relative minimum happening at x equals negative 4. So I'm going to say that this is false. But now if p is odd, then I think this is going to end up being true. Because if that's the case, then f of negative x is the negative of f of x. It would have symmetry across the origin. So it would probably be, I don't know, about down there. And yeah, it would go upside down when it flipped across the origin. So I would say it's probably going to look like about that. And yeah, that's going to be a relative maximum. So I'm going to say that is a true statement. All right, now the last examples I've got for you is just a kind of an is it possible? And so I'll try to draw you some pictures here for the ones that are and explain why for the ones that aren't. So is it possible for an odd degree polynomial to have a global maximum? I'm going to say no. That's going to be impossible because we know about the end behavior about an odd degree polynomial. Right, so an odd degree polynomial, at least on the outsides, is either going to look like this if it's got a positive leading coefficient, or it's going to look like that if we've got a negative leading coefficient. And either way, there is no absolute maximum because it's like, if you thought that was the biggest, well, that arrow indicates, well, it just keeps going up, if I go farther to the right or farther to the left. So it's not going to be possible for an odd degree polynomial to have a global maximum. Because a global maximum is the value of x, or it's bigger there than anywhere else on the entire graph. Okay, but it is going to be possible for an odd function to have a global maximum. And I actually have already drawn you a picture of this happening in this video. Right, so I went and grabbed it from the first page, and it was this thing. I think it was x over x squared plus 1. Okay, that point that I just drew at, that's a global maximum, also called an absolute maximum. Global, absolute, same thing. And so that it is possible. That's an odd function. It does have a global maximum. I just wouldn't want you to be confused there. Okay, is it possible for an even function to not have a global minimum? Well, if you think about like y equals x squared, that's an even function. Okay, but it does have a global minimum, and you could have like, maybe something that was, looking like that if that was perfect. That would also have a global minimum somewhere. Okay, so these even degree polynomials with positive leading coefficients. But what if I just let it have a negative leading coefficient, right? Just went like that. Okay. This one would not have a global minimum because, if I thought I found it right here, it's like, oh, that arrow means it just keeps going. It's going to go farther. Okay, so this one does not have a global minimum. So, yes, it is possible for an even function to not have a global minimum, provided it's an even degree polynomial with a negative leading coefficient. That will happen. And the last question, is it possible for an even degree polynomial to not have a global maximum or a global minimum? And that's not going to be possible. And that's because if you think about it, like an even degree polynomial is one that has, what am I saying? The end behaviors are the same. So they either both go up, and you're going to have weird stuff happen in the middle, but they both go up eventually. That does mean that we have to have some lowest point. Or maybe they've got a negative leading coefficient, and they look kind of like that. Okay, I think that's a little sharp, but that could be an even degree polynomial. I think it might just be really high degree, have some weird stuff going on in it, and that would have an absolute maximum somewhere. Okay, so it's not going to be possible for an even degree polynomial to have neither. We got to either have one or the other. And yeah, I think that's going to be all the examples for these notes, and so that's going to be all for this video. Thanks for watching.